All right, last part of looking at reflection and refraction. We're looking at applications with it and things that we can use with our reflection and refraction. So we're going to be talking about critical. We're going to be talking about fiber optics. We're going to be talking about some diffusion of light, different things like that. It shouldn't be too long. Okay, here we go. So total internal reflection. So if you go from an object that is more optically dense to an object that is less optically dense, okay, what ends up happening is that your angle of incidence going in and your angle of refraction coming out, the incident angle is going to be smaller than the angle of refraction. Okay, so you see down here with this example, you can see that as the incident ray comes in, and that theta 1 is smaller than theta 2 as it's coming out. If you move that incident angle far enough, what ends up happening is that it'll hit a point where it will hit that new medium, and then it will run basically parallel with the line. So that angle of refraction is 90 degrees. And so you don't have any of it escaping, it's just staying along the edge. If you go even further of that angle, so if your angle of incidence becomes even larger than that, where it's already past that critical angle, then you have what's known as total internal reflection. So no light has escaped, and everything has just been reflected backwards, back into the object itself. Okay, so that is total internal reflection. Okay, and that is just if you hit it at an angle enough, it stays. Okay, so your critical angle, which we mentioned, is when you have an angle that runs into it and then it ends up going parallel along the medium. So to find what that angle is, so this example from water to air, if we wanted to find what that angle was, we would just use Snell's law again. Okay, so it's the medium of the incident, which is 1.33. The angle, which is what we're trying to find, how far of an angle do we have to move down until we hit that critical point. So sine theta is equal to the new medium, air's is 1.0003, times sine of 90 degrees, because if you have that critical angle, you have created a 90-degree angle with the normal. Remember, the angle of reflection and refraction is based off of the normal, not of the boundary line of the mediums. So it'd be 90. Setting it through, solving it, you get sine theta is equal to 0.7521, and then you use your inverse sine or your arc sine to find that it's about 48.773. So if you shot an angle at exactly 48.773 degrees, light will bounce in onto that change, and then it will run parallel with the changing of the mediums. Now, it's very hard to do that by hand, but you can. If you move any closer back to the medium, or not medium, to the normal, if you move back closer to the normal, you're going to end up having some refraction going through, and it's going to basically start opening up from the medium line. If you move the opposite direction, so if you were at your critical angle and then you made your angle even bigger, what would happen is that it would turn into total internal reflection. So all the light or whatever it is that you're reflecting off of it will just come bouncing back with the angle of incident and the angle of refraction. Now, this is used in fiber optic cables, okay, which is essentially, it's a large glass tube surrounded by more glass, okay, and light is shined through it, and they use binary, I think it's light on is 1, light off is 0, and it flashes real quick, and you can transfer it, and then it takes the 1s and 0s, and then computers use it to basically speak with each other, because that's how computers have done stuff. But what happens is that they take a long glass tube, and then they surround it with more glass that has a very low index of refraction or refraction surrounding it, so that critical angle is a fairly large or fairly small angle. And if you can get a small enough angle, what ends up happening is that as that light is bouncing and hitting it, you get that total internal reflection. You don't have any of it escaping. It's just bouncing, staying in it. So you can have it bend, you can have it turn, and as it hits it, it's just going to reflect off of it again. And you keep internal reflection on. And so that's what you do is you have a medium that is a fairly high index of refraction, and then you surround it by something that has a very low index of refraction. And by using both, you're able to keep it within the tube, and then it goes all the way through. Okay, it doesn't escape from it. All right. Also, with refractions, we have like mirages and looming objects. Basically, light rays can change by using the air around it. So, warmer temperature, it kind of bends it. Okay, warmer and colder temperatures. So that's how mirages are. Is that you see something on the ground, you know, oh, there's water on the ground, when in actuality it's probably a cloud up in the sky. But as those light rays are coming towards where they would normally land and what you would see, those light rays get bent, okay, because it's changing medium. So you have refraction occurring because it's not just the air, it's also temperature. The atmosphere is thicker down here than higher above. So as it's moving, that angle of refraction is basically occurring all the way through, and it can curve, and something that isn't where it is, you think it would be located, which is essentially what a mirage is. Okay, and same thing with looming objects or looming images is just the opposite. It's floating above than below. Okay. Dispersion of light. So this is just when you have light rays, white light hit something and you see multicolors come out, usually water is an excellent example of this. So as it runs into it, because of the different light rays, it separates it out, and then it has its reflection coming out. So that's how you have your different rainbow colors coming from. Just like one drop of water, you can see the rainbow from it, is because the wavelengths get separated from that white light, and when they get separated, they bounce through, angle of reflection going through, and they exit at different points. And so you have all the blue light coming here, and then all the yellow light, and then all the red light coming as it moves across. And so as it moves across, that's what we see. Is just kind of the group. So it goes from white light into whatever it is, and it's just dispersing that light and separating it out into its separate rays, and then they separate each other, and you can see them. All right, that's the end of chapter 17. You're done.